Okay, Zaid, you've asked a question. A solid non-conducting sphere of radius capital R is having a charge density rho equals rho naught x, where x is the distance from the center of the sphere. And we have to calculate the self-potential energy of the sphere. So first let's define what self-potential energy of a charge distribution is. So self-potential energy of a charge distribution is precisely the work done in assembling the charge distribution from a situation in which they were all infinitely separated. So if all the charges were infinitely separated, what is the work that you do to actually assemble the charge distribution that you are considering? So we will do this by assembling the sphere one concentric thin shell at a time, starting at the center. So first let's consider a shell of radius r and thickness dr as shown in the diagram with the two green lines, the red circle indicating the entire sphere of radius capital R. Now the volume of the shell is 4 pi r squared dr, and since the charge density is rho naught r, because r is the distance from center, the charge contained by the shell will just be the product of these two quantities, which turns out to be dq equals 4 pi rho naught r cubed dr. So now we know what the charge contained by the shell is. So now if we consider the sphere that is just inside the shell, that is a sphere of radius small r, you can find out what is the entire charge that is contained in that sphere. And that would be qr, which I obtained by integrating the previous expression 4 pi rho naught r cubed dr between the limits 0 and small r. When I do that, I get pi rho naught r to power 4. Now the potential at a point just outside the sphere and therefore within the thin shell would be Vr equals to kqr by r, which when I evaluate turns out to be pi rho naught k r cubed. Now the charge inside the spherical shell will be assembled. Okay, so we've got so far the charge inside the sphere of radius small r. Now we are going to assemble the charge in that spherical shell, which has an inner radius small r and a thickness dr. The work done now would be dw equals Vr dq. And so I've got the expressions for Vr and dq. I multiply both of them. So pi rho naught k r cubed, that is Vr, 4 pi rho naught r cubed dr, and that is dq. I multiply the two, and what I get is 4 pi squared rho naught squared k r to the power 6 dr. This obviously is the increase in the self-potential energy of the sphere. And so we can just say that that is du, the increase in self-potential energy, which is 4 pi squared r naught squared k r to the power 6 dr. And now to find the total self-potential energy of the sphere, what we do is we integrate this increase in self-potential energy between the limits 0 to capital R. So we integrate that, and what we get is 4 by 7 pi squared r naught squared k capital R to the power 7.